Today we will be focusing again on magnetism. This is part 2 of your magnetism notes, so you'll want to get out the same document that you used to get the part 1 notes, those guided notes, that Google Doc, and we will finish those off right now. So today's focus and learning target is learning target number 3, that you can determine how Earth's magnetic field exerts a force on objects. So first off, we need to talk about how Earth has a magnetic field and what creates it. So Earth's magnetic field is actually the result of the heat transfer from the Earth's inner core to its outer core, which is, as you remember from Earth science earlier this year, is composed of molten iron and nickel metal that convex. Remember those convection currents? That combined with the fact that the Earth itself is rotating and kind of that spins the molten metal inside, and it generates electric currents, which in fact produce our magnetic field. So let's talk a little bit about compasses here. If you're a scout, you might have a leg up on this. First, we'll look at a video on how a compass works.
Right, so here I have a standard compass, just a little plastic compass. If you haven't actually used a real compass before, how it works is there's your needle, there's a red, on this one it's red, the north needle, and there's the south needle. And what a compass actually is a little piece of iron in here that is freely hanging. You need a low friction environment in there, and it will align with the Earth's magnetic poles. So if I want to know where geographic north is, I'm going to spin around the base of the compass. You notice the needle kind of stays the same way until I have the north lined up with the red north facing needle. So right now I have my compass pointing towards geographic north. Next, we want to figure out what magnetic pole is at geographic north. So if this red needle is pointing to geographic north, and that is a north, this is a mini compass in here, if that is the north pole of my compass, to figure it out, I can use another magnet that I know the north and south pole of. And this is just a magnet that has south on one side and north on the other inside a plastic wand here. So if I want to test this out, I'll try this out, and I'll bring my north magnetic pole up to my north red needle, and we will see what happens. All right, so here I come in from the side. Ding, ding, ding. What's happening? Lo and behold, it swapped around, didn't it? That's because opposites attract with magnets, right? So my south pole on my compass is wanting to point towards the north pole of this magnet. Now, let it go back to how it wants to be, realigning with Earth's. So I've taken out this other magnetic field, and now it's lining back up with Earth's magnetic field. Now I'm going to try the same thing. This time I'm going to bring in the south pole of my magnet. Let it reacquaint itself. All right. So now I'm coming in with the south magnetic pole facing it, and lo and behold, it stays, right? So what this tells us is that in Earth, the south magnetic pole is geographic north. I'll say that again. At the north, if you went up to the North Pole where Santa is, you would be going to the magnetic south pole. And again, this is because opposites attract. So if this is my north pole of this magnet here, of my compass, it's going to want to attract to the opposite, which would be the south magnetic pole.
In there. So the north pole needle of a working compass points to geographic north, as you know. And because the compass needle is a magnet, and with magnets opposite poles attract, then the geographic north must be magnetic south, which is what you just saw explained in that video. I know, it's kind of crazy. So here's another diagram I find really helpful to kind of explain how this all works. Again, showing that geographic north is truly magnetic south, and that, you know, your compass points to geographic north. But again, that is magnetic south because opposites attract. So next we're going to look at the compass rainbow. I want you to kind of look at this diagram and think about, what do you notice about the arrows of the compass and how they work? You should notice that the arrows follow the magnetic field lines. Again, opposite poles attract and like poles repel. So we are seeing that also working here with this compass in a rainbow around a magnet. And here's another diagram again showing you that it aligns with the field lines as you see in the video. And finally, one more, if you were to put a ton of compasses around a magnet, you can really kind of imagine if you were to kind of draw lines, how they would line up with the magnetic field. All right, so here is our compass rainbow setup. It's unfortunately, I don't have a bar magnet here at home to show you this, but this works the same way. So on this side of the magnet, this is the north side of the magnet, and on this is the south pole of the magnet. And you can notice here, sorry, it's a little glary, how the compass needles are aligned so that we have that opposites attract. Now, another cool thing about this is that the compass needles are aligning with the magnetic field lines. So you could imagine the field coming out and around and back in. And here again, going out and around and back in. And then this one's stuck in the middle because the field lines would be going out and around, yeah? So just something cool to note. Again, I have my north being attracted to the south pole here and my south needle being attracted to the north there. So, yet again, a compass aligns to the magnetic field that it is in. If it is not near any other magnetic field, it will align to Earth's magnetic field. So that's why you want to avoid bringing other magnets, and electronics have magnets in them. So if you have a compass that is near an electronic, it's going to pick up that magnetic field rather than Earth's magnetic field. Hi guys, we're going to make a MacGyver compass here today. So if you wanted to do this at home and you have these bare minimum materials, you can do this. I have here like a plastic bottle cap, I think from a little mini Gatorade. A poker chip would work well as well. And this is a piece of steel from one of those jumbo paper clips. I just kind of bent it until I got just the straight segment. A needle or a straight pin would also work. Anything that's made of steel would work pretty well, and that's lightweight. And then I also have here, I'm using a pie plate, but any old bowl filled with water would do. And I have it with water so that way things can freely float in here. And then finally, this might be the hardest thing to get, would be a magnet. A refrigerator magnet should theoretically work. I'm gonna just use a cow magnet. It's a little bit stronger, so it should work feasibly a little bit better. But theoretically, if you have a refrigerator magnet, you should be in good shape. So to start off with, I have my piece of steel. This has magnetic domains that are currently not aligned, so they're canceling each other out, so it is not a magnet yet. But we can turn it into a temporary magnet, kind of like I showed you with the paper clips. If I take a pole, which will be the strongest part of this magnet, and I'm going to kind of stroke the piece of steel here, kind of aligning those magnetic domains so that they all end up pointing in the same direction. All right, so once I've done that, I feel pretty confident that I've turned this into a temporary magnet. I'm ready to test this out. So I'll take my cap, I'm going to place it into the water here, and then I'm going to carefully place my steel piece on top of it and let it float. If it's working, this should then align up with Earth's magnetic poles. If I've taken the other magnet away from it, so it shouldn't be interfering with it. And if this is working, it should settle to point true north. Now the tricky piece is if you don't know whether what is the North Pole and which is the South Pole, but it should at least tell you north versus south. Now I have a magnet that I have the bars labeled on, so we can test this out. This magnet here, I have the south on one side, the north on the other. If this is working, if I bring the south magnetic pole to it, it should stay the same, meaning it's pointing towards geographic north, which is magnetic south pole of the Earth. So let's test this out and cross our fingers. Behold, it seems to be working. Now to really test it out, if I bring now the north pole of my magnet here, of the bar magnet, this should flip around. So let's see if that works. Bringing now the north magnetic pole to it, does it flip? Ooh, just like a good old magic trick, it flips and then some,
and eventually it will want to attract because, again, it's being pulled by that. The reason this works so well is it's floating and it's kind of creating a kind of frictionless environment, not completely, but close enough. So if you ever find yourself lost in the woods, like Kristoff from Frozen 2, you can make yourself a MacGyver compass and find north and south.
That's all, folks.